The contaminated gas stream is fed into the tower. Inside the tower is a bed of special packing material. Nozzles spray scrubbing liquid on top of the packing material, and the liquid works its way down the tower. As the gas passes up through the packing material, the particulate and gas molecules come in contact with the film of scrubbing liquid on the packing. The contaminated liquid drains down through the packing material, past the packing support, and out through the bottom of the tower. The gas stream flows out through the top of the packing material, past the nozzles, and through a mist eliminator before exiting the tower.
Did you see it clearly? Are you able to view the video and hear the explanation? Class? Are you able to hear the video and hear the explanation? Hindi audio miss, hinay audio miss, but kitaon. Oh, okay. Thank you, Aliana. I will wait. We'll check. We'll pause again.
The bubble cap tray was the most used device through the 1940s and early 1950s. An amazing number of them are still in service. The tray consists of a riser with a cap on the top. The vapor flows through the riser and around the cap and contacts the liquid as it flows across the tray. The one unique advantage of the bubble cap is that it provides positive assurance that there will be total vapor-liquid contacting without bypassing of the vapor. Their main drawbacks are due to the complex cap design. The caps present an obstruction to liquid flow, particularly in high liquid-loaded towers. Also, a large fraction of the vapor phase pressure drop is wasted, as it occurs in the reversal area between the riser and the cap, where it does not enhance the mass transfer. The labor cost of assembling the riser cap units makes these trays more expensive. The weight of these units also leads to support problems on large towers. Consequently, most new applications today are in services where a large amount of vapor must contact a relatively small amount of liquid. Sieve trays have also dominated tray column design over the last 40 years. Liquid flows across the tray surface, and vapor flows up through the tray holes. The area above the tray surface is a turbulent froth as the vapor and liquid mix. They are the simplest design and hence are relatively inexpensive. Vapor pressure drop is also minimal, as there is no resistance to the vapor flow from valves or caps. Disadvantages include liquid weeping down through the holes and entrainment at high vapor rates. This results in a lower operating range. Valve trays, along with sieve trays, have dominated for the last 40 years. Valve trays generally are proprietary and contain movable valve units. When the vapor rate is low, the valve partially closes and minimizes weeping by restricting the liquid flow through the tray holes. At high vapor rates, the valves deflect the vapor flow. This reduces entrainment by creating a weaker vapor jet and results in a greater operation range. The valves do contribute to vapor pressure drop, as the vapor must push the valve open.
Okay, so hopefully you can now distinguish. I will share this again anyhow. You can distinguish the three different uh, openings of the trays in terms of efficiency, and which one eliminates, if not reduces, weeping and entrainment. Now, those videos, by the way, are also available in YouTube for you to view. Now, we're already done with using material balance equations. That way, we can determine the solvent requirement, the optimum solvent requirement, the trace in our column, or the stages in our column. Now we're ready to do into designing the column itself. So the first part is all into application of material balance equations and equilibrium equations. Now we are into determining how large a column we need and how high a column we need for a particular separation. Now, in determining the column diameter, it is anchored upon the concept of flooding. So we can determine when the column will be flooded, and we will base our design on how big a column we need. That way, it will not be flooded. So in this particular slide, we will be discussing the pressure drop, the flooding velocity, and the tower diameter for a particular pack tower. So there's also flooding in the case of tray tower, but this one is limited. This application is for the pack tower. Again, I will emphasize that when we need to design a column in terms of its diameter, so designing it in terms of height is totally different than the diameter. It is based upon the condition of flooding. So when we determine when the column is flooded, and based on that flooding condition, we want to do away or go away from that particular concept of flooding, and as such, we solve for a condition that is away from flooding. Now, the usual design is for us to use 60 to 80% of the flooding velocity. So we determine when the column will be flooded, and we use only 60 to 80% of that flooding velocity. That way, we can determine the diameter of our column. Now, related to this flooding velocity is the flooding pressure drop. So during flooding, there's a corresponding pressure drop in our packed tower. So the change in the pressure at flooding is caused primarily by the flooding itself. Okay, so its formula is dependent on the packing factor, this F sub P. So it's the only thing in which your delta P, the change in the pressure or the pressure drop in the column, is dependent on. Now, speaking of delta P, how are you going to, or where are you going to get that delta P? So I will go to that particular table in a little while. So in determining the column diameter and the pressure drop, it's important for us to get the packing factor. The packing factor is dependent upon the type of packing that you use. So in the table that I'll be showing to you in a little while, these packing materials are clustered. The cluster for the random packing material is on top. The cluster for the structured packing material is at the bottom. And the way they are grouped, you can already see in the column, one of the columns, the packing factor. After knowing the packing factor or taking it from the column, we solve for the delta P at flooding. So this is already the corresponding drop in the pressure when the column is said to be flooded. Then after that, the third step is to find corresponding flooding gas velocity using the pressure drop correlation. So this is the usual value of the velocity at flooding condition. However, we will determine this particular velocity based on the problem, the condition in the problem that is given to us. Now, based on this flooding condition for the column, we will choose the diameter such that the gas velocity is about half of this. Now, this is class the conservative procedure of designing our column, we use half of the flooding velocity. In our case, and even if you're going to read McCabe and John Copley's, the design of most columns in the industry is not based on half, but rather 60% of the flooding velocity. So if this 50% is already conservative, then they want to raise it a little bit from that flooding, from that conservative assumption of the flooding velocity. So we use 60%. So take note, not 50%, but actually, as you have read here in the first slide, it could be even up to 80%. But most of the books uses the 60% multiplier or the zero point 0.6 multiplier to the predetermined gas velocity at flooding. Then we find the pressure drop in the column for pressure drop correlation. Now, the table that I mentioned a while ago regarding where we're going to get the packing factor is this table. And this is just a a small table, but what you have in your handbook, I think, is if I'm not mistaken, a 5 or 6 page table. It has a more comprehensive list of random packing materials and structured packing materials. I got this one from Jen Kuplis just for the sake of illustrating how to get the packing factor. So in here on the second to the last column, you'll be able to get the packing factor. The first set of value here is in per foot. The second is per meter. So you choose a value depending on what set of units is your problem working on. So in terms of the packing factor, so you look for the particular packing material mentioned in the problem. If the size is given, so you have to choose the correct size, of course, then get here the corresponding packing factor. So this is where you're going to get it, and it's just a matter of substitution to the formula for the delta P, and that's the corresponding pressure drop at flooding. Now, in terms of pressure drop correlation, what you have here actually is the pressure drop correlation for random packing, and you have a different one for structured packing. It's the same thing in your handbook. I got this from Jan Kuplis, but this is, of course, the exact thing that you'll be seeing in your handbook. Don't forget that you'll be seeing a different table or a different graph for structured packing and a different graph for random packing. What you have here on the ordinate is the flow parameter, and it constitutes the flow rates, the liquid and gas flow rates, and the density of the gas and the liquid. Of course, your liquid will be your solvent in the case of gas absorption, and your feed is your gas. Okay? The densities are given in the problem. If not given, you ought to get it in the appropriate property table based on the working temperature or the temperature that is given in the problem. If the temperature is not given in the problem, the working temperature of the equipment, then you can assume room temperature. Now, if you recall, you have this particular formula for the delta P at flooding. So you're going to use that delta P at flooding in here. So this is your delta P at flooding graphs. They are not equally spaced. So if the value of the delta P that you have solved based on the packing factor is not any of these graphs, then you just need to approximate the curve where that particular value that you got from your computation came from. Then using that particular value here for you to approximate your curve, and using this computed flow parameter, you'll be able to get here, or you'll be able to solve for the capacity parameter. Actually, you're not solving because you're reading. So from the value of the flow parameter, you go up to the appropriate curve, for example, 0.25, and read here the capacity parameter. So this is not yet being solved. But from the capacity parameter, that's where you solve the flooding velocity. You see this? This is your linear flooding velocity. That tells you this is the velocity of your streams, gas and liquid, wherein the column is already flooded. But specifically in this case, since this one is labeled as gas, this refers to the linear velocity of your gas when the column is already flooded. By the way, the subscripts here, class, represents the phase So L for the liquid and G for the gas. So if you have read already the capacity parameter here on the vertical axis, you just substitute the values of the densities here and the packing factor again. And this one is the kinematic viscosity, in Centi-Stokes, the kinematic viscosity, which will use your viscosity and density for its value to be known. And if all this data, density, packing factor, and kinematic viscosity were already determined, then with the value that you have read here, you can determine already the linear velocity of the gas when the column is flooded. You use this linear velocity in determining the gas mass velocity at flooding. The gas mass velocity at flooding then will be multiplied to 60% of its value so that we can determine the diameter appropriate for our column. That's for the procedure in determining the diameter of our column. Now, so this is for the structured packing material. And if your column is a tray column, so this set of procedures that I have given you here and the table and the graph that we're using is for a packed column. Okay, this 5-step procedure. If it's a tray column, you'll be using a different formula. So you are to determine the tray factor in this procedure for a tray column from a figure. The figure will be shown in a little while. And you are to find the entrainment gas velocity from equations 11.5-14. It will be shown to you in the form of a sample problem. This is based on fair correlation. Actually, that equation I have already written here. The case of V that you have predetermined in number 1, you will place in here. And with this is the interfacial tension, the in dyne per centimeter. Most often, its value is 20 dyne per centimeter for organic liquids and 72 for water. So this is your interfacial tension. And you have again the densities here of liquid and vapor. Typical value of this for tray towers wherein you are already, the tower is said to be already flooded is 3 meters per second. Quite comparable to that in the pack tower. In here, it's only actually 2 meters per second, even lower than the tower is already considered to be flooded. So the pack tower is a little more conservative than your tray tower. Then you choose a diameter so that your gas velocity is only 70% of this one that you have computed from procedure number 2. 70%. But this is higher. But though 70 is in between 60 to 80 in packed columns, but let's make it uniform to be whatever is the value that you have computed for the maximum linear velocity, that should be multiplied by 0.7. That way you can design your column based on 70% of the flooding condition. This is already the flooded condition. So you're only going to use 70% of that. The pressure drop usually much larger in packed columns. So we expect the pressure drop for tray columns to be larger. And it was even mentioned in the video because of the pressure drop for gas to pass through the liquid on trays. So your delta P here actually constitutes the delta P at dry condition plus the delta P caused by potential energy, this rho GLH here. The rho sub L, this is L class, this one is subscript, not multiplier. Rho sub L GH. So that's your delta P. Delta P caused by the column of liquid itself inside the tray tower, added to the delta P at dry condition. Okay, pressure drop through holes of the tray when it's not yet flooded. And H is the sum of the liquid levels on all trays, which is about 10% only of column height. So if you could see in the formula here, this is actually related to potential energy drop and also related to, of course, pressure. So in this case, rho GH here, the H here is already considering the height of the liquid, as I have already mentioned a while ago. Okay, this is in the case of the tray tower. As for the pack tower, you have a 5-step procedure in determining the diameter. Now, for a tray tower, this is how you determine the case of V. The spacing is most of the time stated in the problem. If the actual spacing of the trays is not the values that you are seeing here, then you are also to approximate the curve that that particular value will fall into. And this one, the ordinate, you will solve based on the flow rate. So this is your liquid flow rate, this is your gas flow rate, and these are the densities of your vapor and your liquid. Using this particular estimation by FAIR, you'll be able to get the K sub V that you will substitute in this formula. A little bit simpler, actually a lot simpler than the procedure for pack towers, because right away you'll be able to determine here the linear velocity, the maximum linear velocity when the column is already flooded, your tray column that is. Okay, now for the column height, you will be using a lot of formulas depending on what data you can work on in terms of the column height. So these particular formulas that I have written is found in this section of your handbook. So section 14. HG and G, HL and L, or the hog, nog, hal, null. Whenever you see the O in the subscript, that's already considering the overall mass transfer coefficient. Overall mass transfer coefficient, where this one is basically based on the each of the trace or each of the stages in your absorption column or stripping column. If it does not have the O, this one is already considering the overall gas mass transfer coefficient or the overall liquid mass transfer coefficient. You should be reading your Jan please and your McCabe. That way you will understand more this particular representation of the HOG and the NOG. Same thing with the HOL and the N with the subscript OL. Now, we use class the subscript G and OG if the problem is gas absorption. If the problem is stripping, we use the L. Okay, because in stripping, your feed is gas and your solvent is in stripping your feed is liquid and your solvent is gas, so that is why you have L here. But in the case of gas absorption, it's the other way around, so you use the HGNG or the hog null in determining the tower height, which is represented as letter Z. Okay, the formula you're seeing here is snipped from Jan please. Okay, the formula that you have here for the nog and the null, which you will multiply to the hog and the hull to get the tower height. I have written here the formula in your handbook where you can get or you can solve the ends and the nog and the null. Same thing with the hog and the hull. So if you have this pairing already, the appropriate pairing, that will give you the column height. Now, for the LUT solutions in Jan please, you have these equations together with this figure to use in computing for tower height using film or overall mass transfer coefficient. If the solution rather is concentrated, then you are to refer to this particular portion in Jan please. This formulas class is in the handbook. So I'm giving you an alternative on what you have in Jan please. As I have said already, you have a lot of formulas here to use. You need to read, that way you will know which particular formula is appropriate for the particular condition stated in the problem. Now, determining the column height using the hal null, hog nog, or the simple HLNL and HGNG is okay. It's an alternative, but you can also solve it using the HETP, especially if your column is a packed column. Now, what does HETP stand 4. It's the height of packing material equivalent to one theoretical stage. In our language, ano kadamol ang imo packing material nga makonsider mo na siya nga isa na siya ka tray or isa na siya ka stage. That is what your HETP represents, especially in the case of, as I've said, packed columns. So if you're using the HETP formula, the value of determining the height of the column is also very straightforward. You just multiply the HETP that you got out of this formula by the theoretical number of stages. The theoretical number of stages which you have learned in the previous meeting. So you multiply it by HETP, you got also the Z. This is an alternative formula if you find it difficult to use the formula for Hog, Nog, or HGNG in the case of gas absorption. But if you notice, by the way, if you notice, the HETP has a formula expressed in terms of the hog. Your HETP actually can be solved using the hog. So what is good about this though is if you have the HETP from the hog, all you have to do is multiply it by the theoretical number of stages. That way you can find the height. If this is already asked by the problem, then you'd rather go for this. That way you will not have to solve for the NOG. Though your NOG, which you will multiply to the HOG, is also solved using the theoretical number of stages. So these are how the formulas in determining the column or the tower height interrelated. So these formulas are also available in your handbook as I have written here. Now, this is same for both packed and tray tower, but when we speak of HETP, it's really for the packed tower because we're thinking of how thick your packing material will be for it to be considered as one theoretical stage or plates. And this is for, you could see this particular symbol, it's for parallel operating line and equilibrium line only. So this particular formula is for parallels operating line and equilibrium line. So meaning, if the problem is not specifically mentioning that your operating line and equilibrium line are parallel, it's safer to use the HOG-NOG or the HGNG formula rather than this one. Although class, based on the, if I'm not mistaken, I have solved a particular problem, computing for a problem, rather one problem, computing for the tower height in 5 different procedures. The variation in the answer is very, very small. So if you're given a multiple type question asking for the column height and you're using, for example, this formula, you're using this formula not knowing or it's not even stipulated in the problem that your operating line and your equilibrium lines are parallel, the deviation is very small. It's really very small. So it will be actually shown to you at the latter part of this slide, that particular set of formula. The sample problem that I'm referring to is this one that solves for the tower height. The answer for this actually, ang akong smiley, naglayo na. The answer for this actually, if I'm not mistaken, is this one. The one that I labeled as C, 1.36. I have included and I have inserted in this slide class. It's not available anymore because I've copied it. But when I place it there, I will make it available. It has 5 different procedures on how to solve the tower height using the different formulas that I have shown previously in this slide. So when I will check later on the one that I have uploaded in Canvas if the PDF that I inserted in the PowerPoint presentation can be opened. If it can't be opened, I will upload it in Canvas. That way you can study it. If you notice, class, I did not include a sample problem on how to apply this particular concept, this particular table, the concept that is, same thing with the graphs here in determining the diameter of the column. Primarily because I want a change in the way we handle our synchronous meetings. So I'd like you to read and study on your own how to solve for the tower diameter based on the principle that I just discussed now. We still have 2 more topics to discuss, and that is humidification, dehumidification using the psychrometric chart, and we still have drying. And I have only 2 weeks left, so I will leave that to you to study. It is in Janku, please. If you're going to ask me which of the 2 books can you understand, you have a good way of understanding the flooding concept related to the diameter of the column. I think John Couples presents it in a very understandable manner. So I will leave that to you to study. In the same way that I have inserted already the PDF copy of the 5 different ways of solving for the tower height for the last sample problem, I have indicated in here because I want on Thursday to start with a new topic. Now, what will happen tonight is I will leave to you the 1 hour, the 1 hour and a half of your dry lab schedule to study the sample problems that I have said to you to study. Fair enough, because I don't give you anything to solve. So you study the sample problem in Janku, please, and you study the solution that I have inserted in this PowerPoint presentation. That would be your task for tonight, or any other time that you can insert this particular set of requirements. So Thursday, I will start with the use of the psychrometric chart. On the dry lab schedule on Thursday, you will have a quiz on gas absorption. And which part of gas absorption? Until determining the theoretical number of stages, including determining the optimum number of stages, because it's just like determining the number of stages, only that you added the concept of the minimum solvent requirement to get the optimum solvent requirement for the said problem. What you will be studying will be given to you next week. And the problem on drying and humidification and dehumidification will be given to you on our last week. I would like to borrow a few minutes of your time. It's 7, probably 5 to 10 minutes. Based on our last 2 weeks ago, we had a departmental meeting. And if some of you have already viewed your course guide for all your subject, it's a guide to the grading system of that particular subject. If you notice, all professional subjects for CHE have a culminating requirement and have a comprehensive exam, which is totally separate from the term grades. So if you have read it, your prelim, midterm, and end term grades are only 20% of your overall final grade. So 20 for prelim, 20 for midterm, and 20 for end term. What comprises the 40% is the 20% for the culminating requirement and the 20% for the comprehensive exam. I will discuss the details of how your grades will be recomputed. The grading system that was originally uploaded by your teacher and by yours truly in the subjects in Canvas, in your courses in Canvas, is based on the premise that we will not have this COVID thing until now. We were hoping that by December, we'll be able to face each other already. And that is why you were given a comprehensive exam other than the end term exam, because when you speak of comprehensive exam, that's from the very beginning. So it's very important that you will be attending the student assembly, because I will address this particular concern, the change in the grading system, to the entire CHE body, because from first year up to third year and fifth year irregular, the same grading system will follow for the professional subject.